In this video, we are going to discuss the term row-echelon form. Now, that second word is, again, it's echelon, E-C-H-E-L-O-N. So what is this? Well, this is the stair-step pattern formed by the non-zero, so all the values that are not zero, elements of a matrix, okay? So there's a few stipulations on what it means to have a matrix in row echelon form. So let's go through these and then we'll do a few visual examples of this. The first stipulation is that all rows consisting entirely of zeros are at the bottom of the matrix. Okay, so for example, if you have a matrix, you know, you have maybe A11, A12, A13, A21, A22, A23, and let's say you have a row of zeros, then that would be at the bottom of the matrix. Okay, so we'll make a little note here. We're going to say row of zeros, spell that a little bit better, zeros at bottom of the matrix. Okay, now I mean that's even if you have a row of zeros. I mean, you may not have a row of zeros, in which case, you know, this point is irrelevant. But if you do have an entire row consisting of zeros, you have to do a row interchange operation and put that row of zeros at the bottom of the matrix in question. Okay, so that's one stipulation if you have a row of all zeros. Okay, the next stipulation is that for each row that does not consist entirely of zeros, the first non-zero entry is a value of 1. Okay, so let's think about this. Let's say we're dealing with rows that are not entirely zeros. So again, let's maybe look at a matrix here. Let's say you have A11, A12, A13, you know, A22. I'm sorry, that's A21, A21, A22, A23, 0, 0, A33. Well, in this matrix right here, for each, let's read it again, for each row that does not consist entirely of zeros, the first entry is a value of 1. What does that mean? Well, that means in this particular example, A33 better be equal to 1, okay? Because again, that's the first in this third row. That's the first non-zero entry in row 3. What else must be equal to 1? Maybe pause the video and think about it. A21 better be equal to 1. And then what else? A11 also better be equal to 1. Okay, so again, for each row that does not consist entirely of zeros, which in this little illustration is all 3 rows, the first non-zero entry, and that's the first non-zero entry from the left, is a value of 1. So you have to have that stipulation as well, okay? So let's go to the next stipulation. So the next stipulation is for 2 successive non-zero rows, the leading value of 1, that's what we just talked about a second ago, in the higher row is farther to the left than the leading value of 1 in the lower row. Okay, so let's think about that for a second. Again, I'm going to do another illustration. If I have, A11, A12, A13, 0, A22, A23, and then 0, 0, A33. Again, this is just another illustration. Then what must be true? Well, what must be read the sentence carefully. For successive rows, successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. So in this illustration here, which values must be equal to 1? Well, here A11 should be 1, A22 should be 1, and A33 should be 1. So basically we're saying these 3 values should be 1, okay? So maybe take a second, rewatch this video, and understand these stipulations. But let's go through a couple of clarifications here, because I know there's a lot of definitions and it can be kind of confusing. Okay, so let's give another definition. We're gonna say what's called the main diagonal. The main diagonal is the diagonal set of entries from the 1, 1 position to the n position, okay? And only what are called square matrices have a main diagonal. And what's a square matrix? What do you think a square matrix is? A square matrix is an n by n matrix. So an n by n matrix, it has the same number of rows as it has columns, okay? So let's look at an example, okay? Let's say matrix A. We have matrix A, we have A11, A12, A13, A14, okay? And then maybe we've got, A21, A22, A23, A24, this is 3, A31, A32, A33, A34, and then A41, A42, A43, A44. So in this general matrix, what's the main diagonal? Well, the main diagonal is the set of entries from the 1, 1 position to the n position in a diagonal form. So it's actually we sometimes call it the symmetric set of entries. So it's this diagonal right here. is the main diagonal. And you see in the previous little stipulation, I kind of alluded to that. And this is an example of a 4x4 matrix, of course, 4 rows, 4 columns, okay? So, so that's what it means to be row echelon form. Now we have another term that's called reduced row echelon form. What is reduced row echelon form? Well, this reduced row echelon form is the form of a matrix where every column that has a leading value of 1 has zeros in every other position. Okay, so basically reduced row echelon form is a subset of row echelon form. Reduced row echelon form basically says that the main diagonal is all ones and every other entry is 0. So let's look at an example of this. Okay, let's say we have matrix A here. Let's say we have 1 0 0 0 1 0 0 0 1. This is an example of reduced row echelon form. Okay, so notice that the main diagonal is all ones, and then notice every other entry is all zeros. Okay, sometimes we call these the upper and lower triangles. Sometimes we call this the upper triangle, and we call this the lower triangle. Okay, so let's do a few illustrations, and maybe pause the video as we go through this so you can help me identify more independently which of these matrices are in row echelon form, which ones are in reduced row echelon form, and which one is maybe neither. Okay, so I'm going to say example. I'm going to say state if each matrix is in row echelon form, reduced row echelon form, or neither. Okay, so let's just give a few options here. Let's say we have matrix A is 1 2 3 0 1 5 0 1 0 0 1. Okay, that's matrix A. Let's say matrix B is 1 -1 2 0 2 1 0 0 1. And then let's say matrix C is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. And then let's say matrix D is 1 0 0 1. Okay, so let's look at these 4 options here under solution. Let's talk about them. Well, matrix A. Okay, take a look at matrix A. Matrix A, what's its size? Well, is a 3 by 3 and is in row echelon form. How do we know it's in row echelon form? Well, notice that the main diagonal is all ones. Okay, essentially, to be in row echelon form, your main diagonal is all ones. Okay, and the leftmost, again, the leftmost entry in each row is a number 1. Okay, the lower triangle is all zeros. Okay, and again, for row echelon form, it doesn't matter what's in the upper triangle. That can be all non-zero numbers. So that's row echelon form. Okay, what about matrix B? Matrix B is not in row echelon form nor in reduced row echelon form. How do you know? Well, matrix B, if you look at its main diagonal, there's a 2 there. There's a 2 there. This is preventing it from being in row echelon form. And if you remember back in the definition of row echelon form, okay, scroll up a little bit, it says for each row that does not consist entirely of zeros, the first non-zero entry is a value of 1. Well, and in our matrix B here, in row 2, the first non-zero entry is the number 2. It should be 1. So this is neither row echelon form nor reduced row echelon form. And then what about matrices C and D? Well, both of these are in reduced row echelon form. Okay, so matrix C is a 4 by 4, and matrix D is a 2 by 2, and both are in reduced row echelon form. Okay, and how do we know? Well, again, we have the main diagonal is all 1s, and the upper and lower triangles in each of these are all zeros. Even though D is pretty simple, it's a 2 by 2, it's still in reduced row echelon form. Okay, so so that's it. That's basically just identifying row echelon form. And what we're going to do is we're going to use this information when we're solving systems of equations using matrices, and that's what we're going to do in the next couple of videos.